Today, we have this honor of honoring people and listening to people who have made a mark of the university at the international stage. Today's program is divided into two parts. The first part, at the international stage in the field of actuarial science, the Sri Sathya Sai Institute of Higher Learning as a university has made its mark at the highest levels possible. So to honor two people who have made this possible, I invite them on stage right now, Mr. Harold Singh and Sri Sathya Sai Mudigunda sir. In the last 1 year, our university, I think each one of us who have been there, our knowledge or acumen, aptitude, whatever you may call it, about the space explorations of the country has increased a bit. Whether it was the ISRO's program which happened 1 year ago, or whether it was Chandrayaan which happened some time back. Today, one such other mission which is going to be, the clock is ticking for them, similarly for us too, is the Aditya L1 mission of the ISRO, of the country itself. And in that, one of the main persons who was involved, we are lucky to have him amidst us. With a big round of applause, I request you to please invite Professor Raghavendra Prasad, our Vice Chancellor, on the stage. Like I said, the clock is ticking, 11:50 is supposed to be the launch. So I will now invite our HOD, Associate HOD, Department of Mathematics and Computer Science, Dr. N. Uday Kiran, to take over the proceedings for the day.
My humble pranams at the lotus feet of our beloved Bhagwan Sri Sathya Sai Baba, respected Vice Chancellor Sir, Director of the campus, Dean of Sciences, the guest of honor, Mr. Harold Singh and Mr. Sathya Sai Sir, and all the heads of department, faculty and beloved students. So as we are awaiting the solar exploration of India, we also have this momentous occasion of International Actuaries Day, and it's my honor to celebrate this very briefly because of the long program we have in this occasion. So September 2nd marks a very important day in the annals of actuaries history. Now actuaries, as all of you know, I just wanted to ask you, because we were just having this conversation, is there anybody in this audience who has not heard about actuaries before till today? So we have only one out of such a big audience. Back in our student days, in my MTech, I have not heard about actuaries. So one of the key agendas of International Actuaries Day is to showcase and reaffirm that actuaries indeed existed about a century back. And they also wanted to reaffirm that this profession, in terms of, be it in terms of risk analysis, data analytics, or insurance, has been at the heart of several professions. So on that kind of importance of or the significance of this particular occasion, we as mathematics department decided to celebrate this occasion by honoring two of our very exceptional dignitaries of our department, Mr. Harold Singh and Mr. Satya Sai sir. Mr. Harold Singh is actually celebrating his 50 years of journey in Actuaries, and so his contributions to create the future Actuaries and his enduring dedication is definitely commendable, and also it speaks of the role of leadership in Actuaries profession. So to speak about Harold Singh sir, we have Satya Sai sir coming to the stage. Sai.
Sairam, respected Vice Chancellor sir, Director of the campus, Dean and HODs, my respected elders here, my dear students. So I'm very happy to be here today to celebrate International Actuaries Day. Mr. Harold Singh, he is here in Puttaparthi. He doesn't belong to Puttaparthi. He was in US in 1997. Swami appeared in dream and he said, okay, you come to Puttaparthi to see. So he came here and he settled down here. From that time onwards, he is here and contributing a lot to the Puttaparthi society. So very few are aware actually of Mr. Harold Singh as an actuary. He did multiple types of service here in Puttaparthi before being recognized as an actuary in 2017 when we started our actuarial program in Department of Mathematics and Computer Science. That's the time we invited, and then he voluntarily accepted to help our students in actuarial program. In 1973, he completed his actuarial fellowship from Society of Actuaries in US. And today it's like we are celebrating along with International Actuaries Day, his 50 years of actuarial qualification completion. So that's the occasion for us. The American Society invited him to celebrate there. We said, sir, we'll celebrate here in Prashanti Nilayam. So we are very happy to have Mr. Harold Singh motivating our students and contributing a lot for our program here. Today we stand as one of the top 4 universities in the world for the actuarial program. So our students, they want to study actuarial program in India, anyone, this is the place to reach. They don't need to go to Washington, DC or any other place. We are on par with any of the top universities in the world, like the Arizona State University, Purdue University, or the Bryant University. So these are the other universities who got this level of award previously. Similarly, recently we got the recognition from Society of Actuaries, and we are the only university with the advanced curriculum in the country, in India. So if you look at the whole map, there are 200 plus various countries in that actually. In India, we are the only university, so it's a Institute of Higher Learning, representing the advanced curriculum recognition from the Society of Actuaries. So these are the top things, even actually that's bestowed on us with Swami's grace. So for all these achievements, and apart from that, we have produced about 65 actuarial students here, and then recently we started in the Ishwarama school, about 20 of them are joining the actuarial students group. So very soon we'll be touching 100. So this itself is very rare to have 100 produced in one place. Is very rare in actuarial science because it's very difficult and it's a long drawn. It's only with Swami's grace it is possible. And Harold Singh is one of the instruments who made this possible at our place. And he served as Senior Vice President He was chief actuary. He was, he started his career with, in court. Then afterwards he realized somebody is earning more. Why he is earning more? He found out. Then he started actuarial science. Then he completed. So he really got to the top of the actuarial profession. So we are honored to have you, sir, here. So we're very thankful for being here. So this is our the best opportunity to recognize Mr. Harold Singh with us. Okay, thank you.
Thank you, sir. So, on a slight personal note, Harold Singh, sir, although I didn't know personally when I heard, but I came to know that actually he's the one who started this Shanti library, which is there outside. And I was one big recipient of that, user of that library. Then I personally felt, oh, that's really nice that sir is doing good service. Sir has settled in Puttaparthi right from 1980s. So he's been an ardent devotee of Swami. And he also had a very close association with Swami. Moving on to Mr. Satyasai Mudgunda, as Satyasai sir, as he is fondly called. So he is one true luminary who has a good blend of actuarial and technology. So I was planning to speak few words about the development of actuaries, but we really heard it from the horse's mouth. So let me take few moments without really taking much time to tell about Satyasai sir and his achievements. So Mr. Mudigunda's leadership has been demonstrated through his management of an impressive 36 large international projects, collectively valued at 25 million US dollars. These endeavors involved up to 500 members per project, bearing testament to his exceptional capabilities. His commitment to the knowledge advancement is remarkable. Sir has earned 5 international qualifications in actuarial science, insurance, and management, including AIAI, PMP, CPCM, INS, API. Sir, having not been contented with the industrial achievement he has made, he has moved on to the academia, and in academia also he has produced 3 PhDs in management and mathematics department, and he has also earned a good number of awards. One of the crowning and a prestigious award is this CAS award, which he won in June 2022. His influence extends to academic accomplishments of his students, as sir mentioned, 65 projects and 36 research papers and several MSc level projects. Of course, these are all related to the actuarial. Sir's contribution is not just related to only a smaller section of actuarial students. Most of us have been a recipient of sir's hard work and efforts. In fact, to recall or reminiscent the time when we went through the pandemic. So one point of time, the question came, how do we go about the classes? And as we were discussing in mathematics department, it was sir who had come up with this LMS, which most of you have actually used. Sir had actually housed that website for us. So we are we are very grateful and heartfelt thanks to sir. And his sincerity doesn't stop there. When university needed good support from university management system, he is the first person to come forward and help the university and play a very pivotal role. So sir deserves a much bigger round of applause for these achievements. Sir also has been active in the spiritual realm. He has been a very active participant in the yoga activities of the university. He has been, actually he had made a curriculum for yoga, and that is also coming as a value added course, along with several predictive analytics, etc. So with these great achievements and kind of contributions which we are all enjoying, we heartfully thank Satyasai sir for his immense contributions to the department in particular and university in general. Thank you, sir.
श्री गणेशा विघ्ननाश गजानना श्री गणेशा विघ्ननाश गजानना
So I would like to invite Pallav sir up for a minute. So because we got the Casualty Actuarial Society Award, Pallav received this in the US. We want to hand over this to University Vice Chancellor. This will be the memento that actually stands in his office as a remembrance for anyone who is coming to his office to see this.
From the domain of actuarial science, it's time to now shift our focus to something more related to physics. And if at all, apart from the Honorable Vice Chancellor in this gathering today, there are some other set of people who understand in little more technical detail about the satellites and about the launch that is happening. It's the students from the physics department. So the senior most students of the physics department, the second year MSc physics students, are kind of going to help those of us who may not really understand too much about what is happening today to understand about the launch of the satellite, launch of the vehicle. So I request students from second MSc physics to enlighten us a bit with their knowledge. I invite them now.
नमः सूर्याय शान्ताय सर्वरोगनिवारिणे आयुरारोग्यमैश्वर्यं देहि देवाः जगत्पते O Lord Surya, ruler of the universe, you are the remover of all diseases, the repository of peace. We bow to you. May you bless us with longevity, health, and wealth.
The captivating dance of energy on our closest star, the sun, which is called the big ball of fire. It affects our everyday life in many more ways that even we are not familiar with. So now, imagine a colossal ball of seething gases where magnetic forces twist and turns to produce eruptions and immense bursts of light and heat. These eruptions, which we call it as solar flares, have the potential to destroy any communication systems, satellite operations, and even the power grids that are on Earth. So, beneath the sun's serene surface that we see lies the world of ever-changing magnetic field that interact in both gracious and chaotic way to produce something called sunspots. Therefore, it's not just like burning a coal or wood, but instead, it's performing a mesmerizing natural magic trick, which we call it as nuclear fusion to create this light and heat.
So, is it possible to study the dynamics of the sun?
Let me tell you some facts. The core of the sun is under extreme pressure and temperature, which is estimated to be around 15.7 million degrees Celsius. Solar expeditions carried out by various space agencies have been studying the solar atmosphere. The solar atmosphere consists of photosphere, the corona, solar wind, sunspot, solar flares, and etc., which makes it extremely challenging for anyone to go on an expedition. The sun releases energy at a rate of 4.26 million metric tons per second, which produces the equivalent of 386.4 septillion watts of power.
How much does that translate in our real world?
Well, to put that in perspective, this is equivalent to 1.8 billion SAR bombs, the most powerful thermonuclear bombs ever built. To answer your question, yes, it is possible to go near sun's atmosphere with a spacecraft to study its dynamics, but it's very challenging. We have to build a spacecraft which would venture as close to sun's atmosphere as possible and still image it without its cameras melting. We have to build a strong shield that will protect the payloads from intense radiations like X-rays and UV radiations.
Plus, there are other challenges too. Like you see, the solar winds, they contain the charged particles. So these charged particles, they exert extreme force on our spacecraft and may destroy its electronics. Therefore, we should be sure that we have proper management and sustainable shielding effects. And also, the vast distance between the sun and on Earth provides another difficult challenges like the delay in the communication signals and the data retrieval challenges.
The solar expedition has been a remarkable journey of human exploration and scientific discovery. Over the past several years, many teams of scientists, engineers, and astronauts have embarked on extraordinary missions to unravel the mysteries of our sun. With cutting-edge technology and state-of-the-art spacecraft, these expeditions have yielded unprecedented insights into the sun's complex dynamics, its ever-changing surface phenomenon, and the fundamental processes that drive its energy production. These have not only deepened our understanding of the solar physics, but also has practical implications for the Earth, in that they help us predict and mitigate the impact of solar storms onto our planet's technological infrastructure.
So, Can you mention some of the solar expeditions that has happened so far?
Yes, here are some notable missions and projects that were part of the solar expeditions. The Solar and the Heliospheric Observatory, the SOHO, launched in the year 1995, a joint mission by the European Space Agency, ESA, and the National Aeronautics and Space Administration, NASA, has provided us crucial data about the sun's interior, the outer atmosphere, and the solar winds, a continuous stream of charged particles that flow outward of the sun's outermost atmosphere, the corona, influencing the space environment throughout the solar system.
The Solar Dynamics Observatory, SDO, launched in 2010, is a NASA mission that continuously observes the sun in multiple wavelengths, greatly enhancing our understanding of solar activity and its impact on Earth.
The Parker Solar Probe, launched in the year 2018, this NASA spacecraft is on a mission to study the sun up close, flying into the sun's outermost atmosphere known as the corona, which extends millions of kilometers into the space with extremely high temperatures. This probe aims to solve the long-standing mysteries about the sun's behavior and its influence on the space weather.
The Solar Terrestrial Relations Observatory, also known as STEREO, launched in 2006. This NASA mission consists of 2 spacecraft that provides 3D views of the sun and its solar storms, helping scientists understand the sun-Earth connections.
The Sun Orbiter, the Solar Orbiter, launched in the year 2020, a joint mission, again by the ESA and NASA, is studying the sun's polar regions and the magnetic fields, gives new insights into the solar activity and its effects on the solar system. Various countries operate a range of satellites and instruments dedicated to monitoring solar activity and its effects on Earth's space environment. These missions have collectively contributed to our understanding of the sun and its critical role in our solar system.
You see, understanding solar dynamics not only unlocks the secret of our sun's behavior, but also sheds light on the broader mysteries of stars across the universe, captivating the imagination of both scientists and enthusiasts alike. So when you look up at the sun, remember it's not just a big ball of fire. It's a self-sustaining nuclear fusion reactor, lighting up our solar system and providing us with the energy we need to thrive on Earth. It's the ultimate cosmic party that keeps going, and we are lucky to be in the front row to enjoy the show.
Today, India is embarking on one such journey after the success of Chandrayaan-3 to create history and carry forward the legacy of India's space adventure. India will be placing a spacecraft in the halo orbit around the Lagrange point 1 of Sun-Earth system. This is not just a mission. This is a testimony of India's space prowess in space research and space technology. We bow down to Thee, O Lord, the source of supreme energy, and pray for the success of India's maiden solar mission, which will unravel further the mysteries of sun and bring glory to our country. Jai Hind! Jai Sai Ram!
Whether it be the deep blue sky during the day or the night sky filled with stars, I think each one of us is always enamored by something that's so celestial, because what lies out there is so unknown that sometimes we wonder that what lies within is known how much. Anyway, today we have with us a person who could have chosen to be at the ISRO today, possibly with the launch of this particular vehicle, but with Bhagwan's grace, we have him amidst us today over here. Professor B. Raghavendra Prasad, let me take this opportunity to introduce him to everyone. Professor B. Raghavendra Prasad studied his MSc from the same university where we are all seated today. He joined the Department of Physics at the Indian Institute of Science in 1986. Back then also, he worked on the Laser Applications Program, which was back then a defense project of national importance. Upon completion of the project, he joined the Indian Institute of Astrophysics in 1998. At the Indian Institute of Astrophysics, he led several complex astronomy projects such as high-resolution Eclipse spectrograph, forgive me if I am wrong, closed-loop adaptive optics. During his time at the Indian Institute of Astrophysics, he established several R&D facilities and its field stations. He set up the contamination control and measurement facilities and protocols for space-based astronomy, and was also a lead member of the UVIT ASTROSAT, which was a mission of ISRO. Professor Raghavendra Prasad was appointed as the principal investigator of the VELC Aditya L1, the space solar mission of ISRO. He and his team delivered the primary payload, which is called the Visible Emission Line Coronagraph, for India's first space solar observatory. The Aditya L1 mission is expected to give new insights into understanding the dynamics of our sun and help develop models for space weather prediction and several other areas of solar astronomy. Aditya L1 is built by a collaboration between ISRO and many Indian research institutes. It has 7 different science payloads to make measurement. Among these 7, the construction of the largest of them is the VELC, which was led by the Indian Institute of Astrophysics, for which Professor Raghavendra Prasad was the principal investigator. The VELC can continuously image the sun in the wavelengths of particular spectral lines in the visible and record spectroscopic data in visible and infrared wavelengths. If we were to go on to talk more about these details, then there is no end to it. But at this point of time, like I said, we are all racing against time to watch the launch of the satellite from ISRO. So I request Professor Raghavendra Prasad to share his thoughts with us today and make us privileged to this moment, because, like I said in the beginning, he could have been anywhere sharing his thoughts about this day. Now, this is a very important detail which I shouldn't miss out. He was actually invited to be at the launch, but then he decided to be here today.
Om Shri Sai Ram. I start my discussion on this very famous mission with prayers to our divine founder chancellor, our Bhagavan Shri Sai Baba, without whose blessings, probably I would not have been here today. So I owe everything to him for all his blessings and guidance all throughout my career and life. My dear directors of all the campuses, the deans, and Mr. Harold Singh and Sai Mudigunda, and all my dearest colleagues and really dearest students. Well, I'll take you through this journey of so-called Aditya mission. Probably I'll be very brief because I'm sure all of us are waiting for the launch. And this is more than 15 years of my work. Any science mission really takes a lot of time. While we were conceptualizing this mission, I was also working on other space-based astronomy observatory called AstroSat, where IEA was again a lead institute for the primary payload. And with that, experience and expertise, we had to start a lot of facilities to build that, what's called Space Science Center, where one of the critical requirements for any of the space programs is to ensure that we maintain the so-called cleanliness. This cleanliness is nothing but semiconductor class. And this is a technology which never existed in India, and even if it existed, it was in a very small pockets, in some specific industries. But I think IEA was the first to establish that facility and get it qualified by various international agencies also to and also establish a lot of protocols which also evolved as we learned from mission to mission. Okay? For example, Aditya mission requires much more stringent conditions as compared to AstroSat mission. So we had to evolve with that. Anyway, I will not go details into that. Now, way back in 2006, there are a lot of debate in astronomy community across the country that we need to have, because IEA established the Himalayan Chandra telescope, and then also the AstroSat project for stellar observations, that was also taking shape in a very nice manner. And then finally the solar physicist felt as why should we left behind. So there is a community of solar physicists, which is a small number in India. You see, the astronomy community is a very small number in India, because astronomy is a challenging field. So you find that in spite of how we talk about it philosophically or even romantically or spiritually, whatever way you want to talk about it, through poems or prose or whatever it is, but still, if you want to really enter into that, either theoretical astronomy, astrophysics, or observational astronomy, or experimental astronomy, whatever it is really, really a big challenge. You need to really have it. So that's why we find that community itself is very small, not only in India, across the globe. Okay? Now, having said that, I'm sure if I could get in, I'm sure anybody here can get inside. So let's be very clear about it. It's just a question of getting used to it. Now, in 2006, we had the first meeting in Raman Research Institute, Bangalore, so where a lot of deliberations happened. We decided that any ground-based solar telescope is a big challenge. Challenge in the sense that it takes time to establish that. Of course, parallelly, we started what's called National Large Solar Telescope Project in Pangong Lake in Himalayas, very close to our Chandra Observatory. So, but at the same time, we had to, that's a big time project, and we said, why not we go to space also, okay? Because space has some very distinct advantages in terms of spectral domains. Because the Earth's atmosphere, as we know, is the greatest protector of life on Earth. If that is not there, life itself is not there on Earth. So that is the one which also sort of, if you want to really explore outer world, I mean, your own, see, this all again, space exploration all stems from the fact that, are we alone? Are there anybody else? What is this all about? How did this begin? Is it a Big Bang theory correct, or is the steady state theory correct? Which is correct? These are all scientific explorations. In spite of, I mean, they are all, very, very sort of, once you go deep into it, you find that there's no actually difference between science and spirituality. They all converge. It's just a question of how we package it differently. That's it. Okay, now coming back to this Aditya project, so then we started proposing we should go to space. And then we met then Professor U.R. Rao, who was also a very eminent physicist, as well as the chairman for ISR for a very long time, and he also was one of the founder directors of physical research laboratory in Ahmedabad. Extremely, I don't know, I have no words to explain him, talk about him, because such a great man. I can only bow my head. So we had several rounds of meetings with him, because he was the chairman of then called ADCOS of ISRO, because now it is called as Apex Board. We had several rounds of discussion, and he really said, yes, we should go forward to it. And he asked us to come out with some concept details. So I had a senior of mine who is an experimental solar physicist, Professor Jagdev Singh, whom I call him as a Bhishmacharya of this solar community in the country. He is almost 80, like Dr. Harold Singh over here. Still, he works harder than anybody, even a 20-year-old. So that's the kind of passion that he has. And under his leadership, a lot of concepts. I was the project manager then to get started on this mission. And then we came out several concepts. There are a lot of reviews that happened, so to cut everything short. In about 2009, it was approved. Only one single payload on a low Earth orbit on a smaller satellite, an experimental basis. So once we started realizing that, then certainly there was a necessary, see, for any serious solar observations, you need to be in a point called Lagrange point, which I'm sure my young colleagues talked about it briefly. So if you have to go there, it's sort of, it's about 1.5 million kilometers away, the first Lagrange point, which is useful for solar missions, where, several of missions they talked about are parked over there, so that you can observe our sun 24 hours without any obscuration. So then we said we should go there. So then the satellite platform, everything becomes, different. It becomes a different, larger platform, because you need to carry more fuel for the mission to, for the, spacecraft to go till there. And the mission life itself, minimum life is about 5 years is what we plan. So there's a lot of these, deliberations go on, a lot of engineering challenges. Everything is worked out, and we said, okay, apart from this primary payload, we'll have some more payloads, okay? Because so far, all the missions they talked about, right now, there's a very little of observations in the visible domain and near UV domains, which is also very important for us, because they are actually what I call spectroscopic imaging, or even the continuum channel imaging channels both, where we have imaging plus spectroscopy, both are built into it. And then we said, okay, at IA, we said, why should we be left behind? We'll rework on our payload, because we had only 3 imaging channels then. Then we met Professor U.R. Rao, and he won't take any of these changes very kindly, because I remember by then Professor Singh had retired, and I had to take charge as a principal investigator. And I had several dressing downs with him, to be very honest, but every one of them was worth it. Every one of them was really worth it, because everything makes you think little deeper, little better, little higher, little more technical, little more scientifically. So these are the things which is very essential. So they have not become so great just because they have not done it, because they have achieved that in a very hard way. So with that, I had to, with several constraints were put on me, saying that you cannot waste the money that is invested already. You need to optimize it with that, and put in all the other channels, because from the imaging, we also had spectroscopic channels which are more quantitative in terms of numbers, okay, for us. Imaging is more qualitative, but to some extent quantitative, but spectroscopy is the one which really gives you what all our young colleagues talked about here, solar dynamics, sun's dynamics. And also the other one is they have been talking about magnetic fields, right? Sun's magnetic field. See, so far no mission has been able to measure the magnetic field of sun, okay, because all the probes they talked about, none of them had facility to measure those things. Okay, in the coronal magnetic fields, what we call, which is the key in understanding the sun's energetics or dynamics. So we packaged what is called first time a spectropolarimetric package also in this payload itself. So that's how the journey began. And then now I'll talk about the payload a little later in detail. Now this is the Lagrange point. What I was talking about, and Lagrange points are the one which is gravitationally at equilibrium between, if you take a two-body problem, I mean, they equilibrate because of the gravitational pull and push between these two, they have some zones where these gravitational fields overlap and they become stable orbits, stable locations, okay? They're called equilibrium points. And of course, the Lagrange was the French physicist who really proposed, all mathematician who proposed this. So if you look at our own, this is our Earth over here, of course, I don't know how clear it is, and this is the sun. So we wanted to park our spacecraft also over here, okay, so that we can observe sun 24 hours continuously with no obscuration whatsoever. Now, regarding this mission itself, it's a first space solar mission dedicated to sun, study the sun, halo orbit, it's called as halo orbit. And again, this distance of 1.5 million kilometers is about 1% of the distance between sun and earth. It's about 150 million kilometers away. And then why study sun? Of course, there are a lot of nice presentation. One is that this is a unique laboratory to test theories of our evolution of stars and formation of galaxies, the entire universe itself. Okay, it's all full of stars, galaxies. I mean, basically stars, right? I mean, you call them in different names based on their sizes, various other aspects. I will not go into details of that. But the sun is the first star closest to us. So we need to understand them before we understand anything else. So that's the one more idea of studying our own sun. Even though people have been studying this for centuries, there is still something what we say, we do not know sun's dynamics, even today, okay? And that's, as they were talking about, is the most powerful particle accelerator because of nuclear reactions over there. And then, because since it's close to us, we can, do a lot of understand better physical through better resolutions, both spatial as well as spectroscopy resolutions. That's the advantage we have in studying our own sun. Of course, I will not go details into this also because they talked about it already. And what I'm going to focus is that the corona, of course, these days corona is a very dangerous word to use, okay? But corona is the most scientific word which was used for centuries. So let's respect that from that point of view. And solar corona is nothing but solar outer atmosphere, okay? Why is it so very important to understand that? Because that is the hub after the photosphere, okay? The photosphere is the sun's surface. Then you have what's called a chromosphere just at the edge of the surface. What we see early morning, sunrise, sunset, or any of this is a photosphere, nothing else, okay? Now, photosphere temperature, my young colleagues talked about 6,000 to 8,000 degree Kelvin. But if you look at it, the outer atmosphere is couple of million Kelvin degrees higher than the surface itself. Our common sense says, naturally, the sun's surface is the hottest thing. No, the sun's core is the hottest, about 20 to 30 million Kelvin degree, Celsius. But it cools off because of radiative transfer and convective transfers, and surface becomes about 6 to 8,000, give or take, numbers fit into that range, okay? But why should the outer atmosphere be much hotter? It's about factor of more than 200 than the surface itself. What is happening over there? And it is this atmosphere which throws up a lot of muck into space, okay? What is called coronal mass ejections, which are nothing but, thousands of tons of charged particles and all kinds of, junk, okay? Which can kill life anywhere and everywhere, okay? And we should be still grateful that we are in what is called a Goldilocks location in the solar system, which is, which sort of meets the conditions that are required for the life to exist, okay? Fortunately, as I said, our atmosphere takes most of this junk, but there are times when our atmosphere gives in, okay? Because if the coronal mass ejections are too very powerful, then as they were saying that, it can kill our communication grid, because these are all charged particles, right? If the charged particles are there, it can kill anything which is, which has opposite charges, or which is anything in, to do with any of these things. Communication systems, power grids, which has happened many times, okay? Unfortunately, India is relatively safer space compared to, Canada or even US, where it's a very routine thing which happens over there, okay? So what we are going to study with this mission is now, all the instruments on that is to study the outer corona, okay, outer atmosphere of sun. Now, outer corona gradually turns into what is called solar wind or plasma, which is also what is called space weather, okay? So predicting space weather is a major challenge. When will coronal mass ejection happen, okay? Can we sort of understand when it's going to happen through other photospheric studies, okay, imaging of surface and various things? Is there some way we can predict that? So once we are able to predict that, can we sort of take care of our space assets? See, we have a space, Indian space assets is about 50,000 crores, okay? And worldwide, if you take space assets, it goes into trillions of dollars. So, recently you found that, heard that, our, who was it, Airtel's, that they have one, they had lost at a time 36 satellites. So the communication went for a toss. Fortunately, they had a backup satellites to take care of the communication network. So that's the, reason, okay. Okay, these are all some physics. I will not go into that because I know that we have students across all disciplines, okay. So the key problem here which this mission is going to want to address is the heating of coronal plasma, okay. Coronal plasma is outer atmosphere. Why is it getting it done? Once we understand that, we understand a lot of things over there, okay. And this is again, every mission, you need to look at what others have done, where are the gaps, okay, what you want to fill in, so that the science is complete. You understand things better, okay. Every mission, in science missions particularly, see, the technology demonstrators are a different thing, okay. I'm not talking about space technology demonstrators like interplanetary missions and things like that. There are technology demonstrators, very little science comes out of that, even though some science instruments are there, but the purpose is totally different. But these pure astronomy missions, say for example, James Webb telescope, they have taken almost 30 to 40 years to build that. Okay, it's in the Lagrange point called L2 on the other side of the Sun-Earth Lagrange point. So that is exclusively meant for deep sky observations, stellar. Okay, so L1 is primarily meant for solar observation. Now these are the what we call the key scientific objectives, which many other missions have not been able. They have given certain data, but there are a lot of missing links in that. So we need to see where we can fill in that and then get that data also possible. Okay, and I just show you one. I think I will not run this video because the students have shown a better video also. This is SOHO data actually, SOHO mission. And so again, coronal magnetic field measurements is something which is critical over here, which has so far no other missions. People have done what's called interstellar magnetic field measurements, but not the coronal magnetic field. So we are looking to measure that also. So this is typically the the Lagrange point, what I talked about, starting from this is our Earth over here, from Earth-centric orbit to the way the spacecraft is maneuvered through what's called cruised into the Lagrange points about 120 days. See, it was actually, there are also called what is called launch windows. If we were to launch some 3 months ago, we were hoping to reach there within 100 days, okay? Because it depends on the positions of Sun and Earth, orbital positions. So it is a lot of calculations that go in it determining the launch periods also. And because of course there are a lot of challenges, you cannot launch whenever you want unless you meet certain criteria. So anyway, the orbital period, what it says is that if this is Sun, if this is Earth, my spacecraft is sitting here and it sort of orbits on its own axis like this, looking at the Sun always, and also rotates around Sun along with Earth. So there's no occultation, what we call, whatsoever. Okay, so you always have it connected with you. Okay, that's the advantage of this. And okay, there are many other payloads. I should give mention about them over here. If you look at the primary payload is the visible emission line coronagraph, which I was fortunate enough to lead that program and deliver the payload from concept to completion. Then we have one more photosphere imaging telescope in the UV band. That's again UV band. Of course, you have LASCO missions, SOHO missions, several missions over there. But this payload again is built by Inter-University Consortium for Astronomy and Astrophysics at Pune. Along with ISRO collaboration, is primarily to sort of image in multiple spectroscopic channels the photosphere of the Sun. Okay, and then we have two other instruments, what are called the solar wind particles. Okay, as I said, the solar atmosphere has a lot of these charged particles like protons and various things. So there are two instruments built by ISRO centers. One is called Physical Research Laboratory at Ahmedabad, the other one is Space Physics Laboratory at Trivandrum. And they have, if you see, they have different energetic codes there. And then we have two more instruments, again built by ISRO centers, which sort of measures the X-rays, okay, in different energy bands. And then we have one more magnetometer, which sort of measures, doesn't measure the coronal magnetic field, it is measuring the interstellar magnetic field at that location. So that's the purpose of this instrument. And okay, I will not go into details of this because these are all, ISRO has been keep flying those instruments very often, okay, many of their missions. Now coming back to why do we need to go to space, again just briefly that, whatever the spectral domains we are talking about, Earth's atmosphere stops it, okay. That's why you find that, here this is where infrared and optical domain we have VELC, then we have SUIT at in the UV domain, then you have X-ray instruments, and you have the particle measuring instruments, and finally the magnetometer over here. And we have various ground-based observatories in the country, so we want to have a complementary science from all of them, the data from all of them simultaneously. Now this is the spacecraft configuration. And what you see here is the topmost one, this purple color, the massive elephant sitting over there. That is the primary payload VELC. Okay, can you see this? I mean, I don't know, it's very clear. And rest of the instruments, you see the SUIT is the next one, ultraviolet imaging telescope, is a much smaller in size, almost 5 times in terms of all parameters. The rest of the instruments are much, much smaller. See, this spacecraft is what is called 1400 class satellite. In that, the mass of the payloads could be at the most, I mean, there's always a bargaining that happens in space programs, mass, energy, budget, everything is I mean, we almost get into real tu-tu-me-me kind of arguments most of the time, okay? And it's like, you are dissected to pieces for every gram of mass and every inch, centimeter of space, and then also every watt of power over there, and every bit of data that you want to, bring in, because that's the limitations over there. So you need to really optimize. It teaches you how to build something which is unique and which is new within the constraints, because the first thing you know is there are constraints. So within those constraints, how do you build that? So that's where what I would say the scientific and engineering discipline comes into picture. More than scientific, the engineering discipline comes into into fore. Okay. So if you see that this is the one, and of course this is a satellite platform, and these are the solar panels. And this is the instrument. I'll talk a little more in detail. These are the the directions. Basically, the positive ER is nothing but towards the sun, and the roll and the pitch is on the vertical to each other, 90 degrees to each other. Okay. Now, this particular payload, which so far no other payload has met these numbers. Okay. One is to look at imaging of inner corona from 1.05 R naught. R naught is nothing but radius of the sun. Okay. In solar physics, use this dimension as a standard dimension, like you have light year, you have this AUs and kind of astronomical units and things. These are the dimensions that we use in astronomy. So 1.05 R naught, I'll tell you why we gave up that 0.5. Otherwise, we want it to be at 1 R naught, means at the chromosphere itself. Why do we want to be there? That is the origin of all the dynamics. Okay. The magnetic field recombinations and origin of flares, origin of whatever you want to talk about, that's the point, okay? Now, why did we give this space 0.5? It's nothing but technological. I'll compare some of the other missions where we are the first ones to attempt that. That's where the actual physics is there for you to understand, okay? And now, we also went into what is called not only the imaging, as I said, we also went into what is called spectroscopy. Again, spectroscopy is very, very quantitative in terms of numbers. And then why spectroscopy? And also why did we choose these lines? Because they're most prominent emission lines. Okay, I'll talk about why that is in terms of when you compare that. See, in the earlier slide, I forgot to mention the coronal light intensity is about 1 million times less than the surface of the sun, if you take the visible spectrum, okay? So you are now looking at separating out the disk light from the coronal light for imaging, because otherwise disk light will mask your coronal light completely and you will not get any coronal information at all. So the payload has to take care of all that, okay? It's a very, I'll not go into details of that, but so we talk in terms of light scattering over here, light scattering in terms of ppms, parts per millions. The highest light scattering we can talk in this payload is about 4 ppm, and other 1 ppm is kept for other budget. So like that, so that demands various requirements on the several of the subsystem what we use in here, particularly the primary mirror itself. And the primary mirror which is used over here is nothing but equivalent to LIGO mirrors. I'm sure many of you would have heard about LIGO experiments. So the LIGO mirror itself, they took about 20 years to make them. And only one company was successful in the country, in Germany. But in India, I'm not saying we are completely successful, but we are almost there. Okay, the science, I talked about science goals a little more in details. And then, okay, these are some of the science goals. And then magnetic field measurement, as I said earlier, at the cost of repetition, we are trying to look at it. And this is what, we are trying to look at in terms of field of view, 1.05 to 3 R naught, and spectroscopy is 1.05 to 1.5. That is because the light falls off, light intensities falls off beyond the measurement limits itself. Okay, and this is the logo that we released. Basically, what you see is a solar eclipse over here, image of solar eclipse, total solar eclipse that was photographed in India by Indian Institute of Astrophysics way back in 1898. Way back in 1988. That tells Indian Institute of Astrophysics is oldest research institute in the country, more than 250 years of existence. Okay? So we are the only institute in the whole world which has solar data, more than 100 years of solar data. Okay? Even then, that is not sufficient to talk about, explain sun. So this is the logo, and these color combinations are because of spectroscopic details. And now, okay, this I talked about a little more in detail. I will skip this slide. And now to compare with the existing ones, what they gave us various, missions. They talked about the students, and the existing ones are, they cover from 2 to 30 R0, where you don't get any spectroscopic information, 0. Okay, no spectroscopy at all. This is what is required over here. So this 2 is replaced by 1.05 for us, and 3 is replaced by 0. 0 is removed over there. So we are extremely close to the surface itself. Okay, and then what we talk in terms of cadence. Cadence is basically light collection durations and various things. Here it talks about more than 10 minutes. We are going into milliseconds. So every event as it is happening, we are capturing it. Our recording speeds are so high. The camera systems are built in such a way that, at millisecond rate, we can collect them. So as it is evolving and propagating, we can, capture every image of that and study. Okay, either way. That's the greatest advantage of this. And then, of course, next I will, now unique features again, where I repeated many times this also. Imaging, spectroscopy, and spectropolarimetry all in one single box payload. And then close to the sun, and then magnetic field measurements. First time we are in situ magnetic, we are making the first time actually. And again, as I talked about spatial resolutions, we are talking about spatial resolution as 1.25 arc seconds. It's the best, imaging. Even your cameras may not have it actually. That's the level of resolution we are talking about. But if I convert this, see, arc second is nothing but is a radial scale of linear distance. If I convert into sun's scales, here 1 arc second means about 2,000 kilometers. Okay, so that's the kind of range we are talking about. All right. So we are collecting at every pixel of 6 microns, collecting that information over there, which is the highest so far anybody has done. And of course, there are many other things. I can go on and on. And the most important thing is that we have an onboard AI-based intelligence, where whenever the CME ejection happens, we can record it as it happens. So as I was saying, that we want to evolve certain predictive models eventually. So that's the reason for this. Of course, there are various other things. I will not go into details. And the system can generate about 2 terabits of data per day. But downlink constraints and all, we reduce it to smaller numbers. And the satellite itself, the demand on satellite, so far, most of the missions they have a few arc minutes of pointing accuracy or stability. And this one here, we are talking about 10 to 15 arc second of pointing accuracy. So it means that we have the control electronic system, total system consisting of sun sensors plus star sensors and the closed loop gyros. So, it's a big mathematical modeling challenge plus realization challenges. So I will just move out, and this is the nightmarish, what we call optical layout. If you see here, it has more than 40 optical elements, 4 detectors, 3 mechanisms, which can be, all of them can be single point failure, and each of them are not off the shelf, each of them are made to design and qualified, okay? And I will just move on because, so this is how the image looks when we really get it as spectroscopic channels, because the center one is masked, this portion is masked, only the coronal light we are collecting it. And again, as you see these numbers, probably we can discuss little more. These numbers are, much better than anybody else. And spectropolarimetry channel, where we can measure few Gauss of magnetic fields over here, because the magnetic field also dies down very fast, so we can measure that. And of course, these are overall specifications in terms of various factors and the proposed science goals. Still, the efficiencies are very, very high when we made, these are the lab measurement numbers I'm talking about. And when we see, when you want to see when the images you get, how do you get that? This is how you get. This is a continuum channel image, what you see, and this is a spectroscopic channel, what we see. And the spectroscopic channel has a scanning mechanism to cover the entire field. Okay, this is how the mechanical structure of the payload, and there is a lot of technologies, new technologies which have tremendously. I think last week when Professor Panchanathan was talking about, there's a question which came, why is anybody spending so much of money in astrophysics and astronomy, okay? Believe it or not, all the technological developments which we use commonly now, in any domain for that matter, started from demands of astronomy and astrophysics. I'm sure we can have a big debate on that still. Okay, that's how spin-offs are what is most important over here. And of course, these are some of my lab facilities which built over several, years, and this is the integration process over here. And you see how the more and more each slide, the payload becomes more and more complex. Okay, and this is the thermal management system. Again, thermal management system is very critical over here because the detectors need to operate at minus 20 degrees. The payload has to be at plus 22, 22 degrees plus minus 3 degrees, because that's the demand of all the subsystem. Each of them we need to meet over there. So a very difficult thermal management system. And then we have a lot of this liquid ammonia based heat pipes, what we call, with thermally wrapped, and also the radiator plates. So there are a lot of design that goes into that and implementation. Okay, these are some of the activities in my lab. You find that, everybody working there, and it's a nice feeling, You start in the morning, sometimes we forget what time we are going out also, and just somebody forces us out, come and have some coffee or tea or snacks, and at least that you have. That's the way we work actually. And this is again, once a payload is built for the calibration purpose, we have a huge vacuum facility in which we are plugging in. And I'm sure many of you who came to my lab would have seen some of these things. Several students and faculty came from physics. I'm sure they would have seen that. And this is the final integrated payload with all the thermal elements, all the controls, everything packaged. See, it has, if you see, I have a model over here, little model over here. It has almost about 16 75-pin D connectors of, harness cables, what we call. The level of control that goes into that. And every one needs to work over. If any one of them fail, everything fails, okay? So that's the amount of planning and execution and testing is sometimes mind-boggling, actually. And of course, this is again, in various, you find that people sitting on the table, sometimes we get some, forklifts coming close by, they had to go on top and do it, all kinds of things people do. This is, finally, it's ready for shipment. And calibration is on dot, like whatever numbers we wanted, we got it. Okay, that's something. And this calibration has to happen only with sunlight. So we have a very detailed, mechanism to get sunlight itself into the lab, and then test this payload. Otherwise, no other lab source will give you the kind of spectral information we want. So that's it has to be tested with sun itself. And then, of course, this is again, I'm not going into details of that. Then we have what is called, not just that, we have to build what's called payload operations center, which there are a lot of observation modes we create, because every astronomer wants his own observation sequence, what science he's looking for, or he or she, let me be gender neutral over here. Whatever they want, we need to meet that, okay? In terms of everybody says, look, I want slit with this, I want this exposure, that channel, this exposure, this channel, this exposure, this data volume and cadence, I want so much, integration so much, and spectropolarimetry, I want at such a long time. So all this, every possible combination needs to be tested over here. And we tested that, and when the data comes down from the satellite, we have to have a very detailed processing center which works 24 hours, okay? And it's a very detailed, from conversion of data from what we call level 0 to level 1 to level 2, and up to level 5, which is science products people can use. And of course, these are all some of the details. I'll not go into that. And yeah, the POC details. And my acknowledgements to all the institutes which are involved here, the lead institute in University of Astrophysics, but various ISRO centers were involved for several subsystem developments. And science, of course, the whole country is involved. Of course, here also the lead is from University of Astrophysics, with the largest solar astronomy community, and various other important institutes. And of course, we had several visitors coming and breathing down on your neck, saying that deliver, 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 deliver. The only word is deliver. No matter what happens, you deliver. We need to meet this schedule. We are slipping the schedules. I mean, Parliament is asking, they are asking, here asking. A lot of such things goes on. You have several who is who in the country coming and seeing that, except probably Prime Minister and President. You have everybody coming there and asking us. So that's another pressure we need to stand. In the sense, one side you need to deliver that works, and there are a lot of development involved. One other side you need to meet the schedules also. So when Vice President had come, I was just explaining it to him, almost pleading guilty over here, and explaining him on the, because we need to tell them what are the challenges over here that they will never understand. So we need to tell them, and then tell them why it's getting delayed. And then they will understand. They are really very brilliant, let me tell you. Once you explain them, they completely agree with you, okay? So that we need to do. So in the lab also I was telling him what the problems are. And of course, you can't make out who is who in this. All of us look alike over here with this, except the sizes probably. This is the team which, my team, I'm very fond of this team actually, which really worked very, very hard in realizing this. And once this was actually sometime in early morning, it was 1 o'clock or something, after we finished everything, they said we'll have a group photo, okay? And that's when it was taken. And of course, they wanted one picture of mine also with that. They said this is very important. And of course, then we had a called handing over, formal handing over of the payload. ISRO chairman was there. And then see the same kind of, miniature model handing over to him, where he had come personally to, take charge of that. And of course, this is a video. I don't think I have enough time to show this video. It's about 5-6 minutes, but I'll skip this. Basically, it gives you the complete 15 years of work in 5 minutes. It takes you through all that, but I think I'll stop here because we have no time over here. How do I stop this? Oh, no. Okay. Now, once delivery, the work actually begins. Much more work is there. What is called environmental qualification test, where the payload will go through all the tests. In the lab we do, and there again in ISRO centers we do as a total system. The space environment is very harsh, and the launch conditions themselves are very harsh. So we simulate, the payload goes through all those conditions, and if it qualifies, means again we do all the detailed tests I talked about and say the payload is healthy and working. It doesn't stop there. Then you have 2 committees here which will sort of make you crawl on all 4, okay? And each of those reviews will happen for 3 continuous days, and you have to really defend my payload is worth flying, okay? Because see, in space there's no scope for failure, okay? There's no scope for failure. And also the model philosophy we took here, see, generally space model philosophy is 3 models. What's called laboratory model, the second one is what's called engineering model or qualification model, third is the flight model. So because of time and financial reasons, we straight away went to flight model over here. So that's even more, people are very critical of you, when we go there. But anyway, fortunately by Swami's grace and all the hard work my team has put in, we are very successful. We passed through all these committees, and then this also before I came, I finished this also at spacecraft level tests. And today is the launch, we're going to see. After that, we still have almost about 1 year of work to say the mission is successful or not, okay? To say the payload is performing as we wanted. One is, of course, cruise phase. If you lose any command, anything happens, it can go off the orbit and you're lost completely, okay? That's very critical. Then we have, after it's parked in its parking space, then you have health checks of the satellite, all its, subsystems, including the transponders, the computers, onboard computers, everything has to be tested, okay? And then after that is, they say pass fail, even if one of them fail, the mission is gone, even though some of these things may be still working. Then we have what's called payload performance phase, which is a very detailed phase for us. Because since ours is the biggest payload, we have about almost 4 to 6 months for that. We do all the tests on that and say whether it's worthy of releasing it to others for observation. Then of course there's what's called guaranteed time, where all those people who worked, they can use it, and then it's open to international community. So this is now, I think one of the points was after was there. These are the after. So this after, we need to wait almost to measure success of this mission from today onwards, almost about 8 months to 12 months. Okay, we should have patience. I think I'm done. Thank you. Sai Ram. Yeah.
PS4 को 2 बार में प्रज्वलित कर यह उद्दिष्ट कक्षा प्राप्त की जाएगी। इसका मतलब PS4 को प्रथम कोस्टिंग फेज के बाद प्रज्वलित किया जाएगा, फिर 30 सेकंड प्रज्वलित रहकर यह बंद हो जाएगा, फिर करीब 1600 सेकंड की कोस्टिंग फेज जारी रहेगी। तत्पश्चात फिर से PS4 को प्रज्वलित कर 472 सेकंड तक प्रणोद उत्पन्न किया जाएगा और फिर शांत हो जाएगा। आदित्य L1 के कक्षा की स्थिति प्राप्त होते ही उसे निर्दिष्ट कक्षा में अंतक्षेपित किया जाएगा। इस तरह पूरे मिशन में लगभग 3800 सेकंड का समय लगेगा।
T-3 minutes and counting.
यह PSLV C57 का प्रमोशन यान ट्रैकिंग के संदर्भ में भी काफ़ी जटिल है। इसे ट्रैक करने के लिए शॉर, पोर्ट ब्लेयर, ब्रूने और बैग स्थित ग्राउंड स्टेशन हमें वास्तविक समय पे यान की जानकारी उपलब्ध कराते रहेंगे। लेकिन चतुर्थ चरण के प्रज्वलन के समय यान हमारे ग्राउंड स्टेशन की दृष्टि से दूर जा चुका होगा, इसलिए शिपबोर्न ट्रैकिंग या शिपबोर्न टर्मिनल को दक्षिणी पैसिफिक महासागर में स्थित किया गया है। वह हमें PS4 बर्न 1 और बर्न 2 की जानकारी उपलब्ध कराएगा। इसके बाद PS4 शट ऑफ और आदित्य L1 के अंतक्षेपण की पुष्टि कुरु फ्रेंच गयाना स्थित ग्राउंड स्टेशन से की जाएगी।
T-2 minutes and counting.
अब हम उड़ान से 1 मिनट 50 सेकंड की दूरी पर। यह PSLV की 59वीं उड़ान होगी और इस PSLV एक्सेल संस्करण में यह 25वीं उड़ान है। इसरो के वर्क हॉर्स कहे जाने वाले इस रॉकेट कई ऐतिहासिक मिशन को सफलतापूर्वक संपन्न किया है, जिसमें चंद्रयान 1 और मार्स ऑर्बिटर मिशन उल्लेखनीय हैं। यह प्रमोशन वर्ष 2023 का 7वां मिशन होगा। इस साल की शुरुआत में SSLV के सफल प्रमोशन से शुरुआत कर LVM-3 के 2 प्रमोशन, GSLV Mark II का 1 और PSLV के 2 सफल प्रमोशन हो चुके हैं। यह PSLV का वर्तमान वर्ष में 3रा मिशन है।
All stations stand by for the time mark. T-1 minute and counting. -55 seconds.
All subs are armed.
-50 seconds.
All sequencers armed.
तो हमारे साथ बने रहिए। अब 40 सेकंड पर
-40 seconds.
प्रमोशन किया जाएगा।
HPP open.
-35 seconds. -30 seconds.
Real-time programs activated.
-25 seconds.
PS2 VSPP open.
-20 seconds.
PS1 ignition RMS arm.
-15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. +5 seconds.
Lift off normal. P1 tracking. P3 tracking.
Magnificent lift-off of PSLV C57 with Aditya L1 on board.
+15 seconds.
PSLV C57 का सफल उत्थापन और इसके साथ
+20 seconds.
प्रथम भारतीय सौर अंतरिक्ष यान निकल चुका है सूर्य के तेज से विज्ञान को प्रकाश करने।
Air lead strap on ignited.
इसके साथ ही एक और कदम है अंतर्ग्रहीय सफर में भारत की उपस्थिति सिद्ध करने का। आप देख रहे हैं PSLV C57। प्रथम चरण पूरी तरह सामान्य।
The rocket flying forth, following nominal trajectory and developing nominal thrust. The bright fumes against a clear midday sky. A rocket launch is more than just a sight to behold. The roaring sound and the vibrations that we can feel here, adding to this, the thrill are just amazing. Ground-lit and air-lit strap-ons operating together with the first stage, S-139.
Ground lead strap-on separated.
जैसा कि निर्धारित है, ग्राउंड लेड स्ट्रैप ऑन को सेपरेट कर
Stage
दिया गया है
performance normal.
और प्रथम चरण का निष्पादन सामान्य है। इस घटनाक्रम में अगला एयर लेड स्ट्रैप ऑन को यान से पृथक कर दिया जाएगा।
Air lead strap-on separated.
जी हाँ, इसकी भी पुष्टि हो गई है। स्ट्रैप ऑन को सफलतापूर्वक पृथक कर दिया गया है।
We are 100 seconds past the launch time. The ground lead and air lead strap-ons have been separated. S139 motor still thrusting.
S139 110 सेकंड के प्रज्वलन काल के पश्चात उसे भी पृथक कर दिया गया है।
Plus 2 minutes.
द्वितीय चरण जो कि तरल नोदक पर आधारित चरण है, इसका प्रज्वलन शुरू हो चुका है और वर्तमान में प्रणोद
Second
उत्पन्न कर
stage
रहा है।
performance normal.
The launch vehicle is at an altitude of 73 kilometers. First stage has been separated. Second stage has begun its operation and the closed loop guidance has been initiated. According to the announcement by Range Operations Director, PS2 is developing nominal thrust.
PS2 41 टन के तरल नोदक पर आधारित चरण है। इसमें विकास इंजन द्वारा 800 किलो न्यूटन का प्रणोद उत्पन्न होता है और इसका प्रज्वलन काल लगभग 150 सेकंड का होगा।
Shar and Port Blair tracking stations presently acquiring signals. Flight path closely matching the prediction.
Plus 3 minutes.
वर्तमान में यान क्लोज लूप गाइडेंस के अंतर्गत है।
Second stage performance normal.
यान की ऊंचाई 106 किलोमीटर तथा सापेक्ष गति 3 किलोमीटर प्रति सेकंड।
The velocity addition in PS2 regime is going to be from 2 kilometers per second to 4.9 kilometers per second.
Payload fairing separated.
The payload fairing covering the Aditya L1 spacecraft has been separated. The current altitude of the launch vehicle is 118 kilometers. Relative velocity exceeding 3.8 kilometers per second.
जी हाँ, यान अब घने वातावरण से बाहर जा चुका है, इसलिए ऊष्मा कवच की जरूरत नहीं रह जाती है और इस कारण इसे यान से पृथक कर दिया जाता है।
Second stage performance normal.
जैसा कि हम जानते हैं, PSLV सबसे विश्वसनीय रॉकेट रहा है इसरो का। वैसा ही प्रदर्शन करता हुआ एक और मिशन PSLV C57 का।
For the present mission, after PS3 completes its burn duration, a coast phase of 200 seconds will follow, in which the rocket will continue to be steered while there is no development of thrust.
जी हाँ, अभी कुछ ही क्षणों में PS3 का प्रज्वलन काल समाप्त हो चुका है और होस्टिंग फेज इसके बाद जारी रहेगा।
Vehicle in combined hosting for approximately 200 seconds.
Unique to this mission, the
Vehicle
PS4
performance normal.
will start twice at predesignated times
Plus
and
7
duration.
minutes.
The multiple start capability of PS4 will be utilized very aptly to achieve the argument of perigee of 346.6 degrees, which is very crucial for this mission. The commencement and duration of PS4 burns enable achieving this orbital parameter. Argument of perigee is the angle that is made by the perigee point from the ascending node at equatorial plane. AOP exceeding 300 degrees is helpful in mission planning to achieve halo orbit around L1 with minimal propellant expenditure.
की ऊंचाई 170 किलोमीटर तथा सापेक्ष गति 7.32 किलोमीटर प्रति सेकंड है।
Vehicle performance normal.
Plus 9 minutes.
Speaking a few words about the Aditya L1, describing the sun, Indian Vedas have said, Yesha Bhagavan Manirakasha Mandalasya Chakravarti Khechara Chakrasya Deepako Brahmanda Bhandasya Asayeva Charkarti Bharvati Jarhati Jagat. This mighty jewel, the light of eastern sky, who generates, operates, and destroys the universe, while the energy of sun, after having filtered by the atmosphere, is available for the sustenance of earth. The explosive phenomena in sun and the solar flares are a cause for concern to the spacecraft and human space missions. The vantage point for such observations is a place in between the sun and earth.
Third stage separated.
Now we have a successful separation event of the third
Vehicle
stage
in
of
separated
PSLV.
hosting. It is approximately 900 seconds.
Plus 10 minutes.
जी हाँ, तृतीय चरण को सफलतापूर्वक
Vehicle
पृथक कर दिया
performance
गया है
normal.
और अब PS4 कोस्टिंग फेज पर है। इस दौरान कोई भी प्रणोद उत्पन्न नहीं हो रहा है। यान प्राप्त संवेग से आगे बढ़ता हुआ और निर्धारित पथ का अनुकरण करता हुआ जा रहा है।
We are 627 seconds from the launch. For another 600 more seconds or so, we will be getting tracking data from the BIAX ground station.
Anyway, now, the launch is fairly successful now. You see that third stage also separating it out, which is very, very critical. And now it will go into the, what we call circular orbit around the Earth, where they do a lot of parameter tests. That will take about another half an hour to 45 minutes for the satellite to be parked into starting orbit, what we call circular orbit. Then afterwards, it goes through various maneuvers before several slingshots are given for it to start moving. It's got several, each of those processes has got several days. And then unless each process is confirmed, they will not go into the next level. So that's going to take time. But what is nice thing about is, as I said, the launch is, clock-like precision and then a very successful launch. I think that's what is very important for us. And the satellite itself, as it is going through, is being tracked by various tracking centers across the globe. And tracking centers of India, tracking centers of NASA and ESA. And also we have, like, you would have heard Ship 1. Okay. So we have several transponders on ships also along the path. So every one of them track that and send the real-time information. That's why they're able to tell you that, where it is now, how it is maneuvering and things. And then, of course, the rest of the images, what you say is simulated based on the data they're coming down from all these tracking centers. So as we see that every tracking center is reporting that everything is nice so far. And the top one which was sitting over there, when I was seeing that, I felt very, very nice. That was my baby, going up there. And sometimes you feel very happy, that, put in so much effort and time and it's work. At the same time, you feel sad also what you built has gone. That's the thing. You don't even have a model over here, So that's the way life goes on. But it's, finally when the science comes out, see, the most important thing is the kind of science we get, okay? I think that's, and the kind of more deeper understanding that it gives us, okay, about sun. I think if you want to really understand sun, this mission alone is not sufficient. Let me make it very clear to you. If you think that it's going to solve the mysteries, no. You need to several hundred such missions. I was just telling, your dean also, you need to have spacecraft at Lagrange point L3 and L4 and also on the L5 other side looking at the sun. Means you have to take complete 360, degree view of the sun because the dynamics can happen anywhere, okay? You want to really understand that. So this is only a starting point. See, for example, Parker probe also, it just touched the edge of outer corona and just went through it. If it were to stay there for a few more seconds, it would have got burnt out. Okay, it's just again the temperatures there are manageable temperatures, what we call probably it's about 100 million kilometers away from sun. Okay, if you're talking about that. Okay, so that's the kind of numbers when we say close to sun, these are the distances. Let's be very clear. I mean, some of our young friends were talking about, close to sun, that there's no technology available which can withstand that heat. What you see, this gold color wrapping over here also, on this what I showed you here, is called multi-layered insulator. Okay, multi-layered insulator which protects heat entering from outside or heat going from inside to outside to maintain the temperature. There's a lot of, this payload has about 200 thermal heaters and sensors for it to maintain its functional temperature. So like that, there are many things that happens. It's a very, very complex thing, and every one of them is controlled. Okay, controlled through onboard computers and also from the downlink stations. So it's all your programs have to work well. Otherwise, you will have some pockets of local disturbance. And I'm sure the people who work in optics or the physics students would know that distortions will set in. Okay. The moment image distortions happen, the data is useless for you. Okay, so no use. So that's why, there's every aspect over here matters. I mean, what you saw, the breadboard, I'm just telling you a number. It's made of solid titanium block. Okay, it's about 1.7 meter in length and 1.1 meter in width and about 80 mm thick. And when I got only 2 pieces of that when we were really scouting for it across the globe. Who will give us this kind of solid monolithic titanium block? Fortunately, there are 2 pieces left in Midani in our own India. Okay, they had as almost like waste pieces they had. Okay, so we could just go there, mark it, send it. Okay, and it took almost 3 years to machine that. Okay, the dimensions remain same, 1.7 by 1.1 by 80 mm. The dimensions remain same. The weight alone reduced, which was almost 800 kilos to 40 kilos. So you can imagine, and it maintains all the properties that I need for further going ahead with this payload. Every property, stiffness, temperature profiles, planarity, okay, every parameter. So that's the level of machining that happens over there. It's a very complex machining, and only one company in the world volunteered to do for us is our own BrahMos Aerospace in Trivandrum. That's the only company which agreed to machine that, and they have taken more than 3 years to do that. So you can understand probably every 1 month, either my engineer used to go or I used to go on to see the progress over there. I mean, it's a very slow process. So like that, I can go on and on and on for everything. How much of, you need patience and, perseverance too. I think that's a very good training program for all of us to develop that patience. Even though at that time we are very, very impatient, but it forces us to develop those good nature, be patient. So otherwise, since there's no choice over there. So like that, even the detector systems, everything. When they say cost of the system, okay, the mission is only so many 100 crores. But if you look at the developmental cost that is put into it later, I mean, either in terms of infrastructure or manpower or man hours, if you want to call it, to put it more quantitatively, runs into, couple of thousand crores. Because even my salary has to be paid, right? All the people's salaries have to be paid and all the infrastructure has to function and everything is, a lot of things are there. But what happens, the experience and the trained manpower and the facilities we develop can meet many more such missions. Okay, that's the whole advantage of the science missions. The science missions demand so much and the spin-offs are, tremendous, mind-boggling sometimes. So, anyway, I think it was a very nice feeling for me, particularly when I was seeing it's going up. And then praying to Swami that it's going to be very successful and we have very good science from it. And the whole world will benefit from understanding our own sun better. Okay?
Sai Ram, brothers and sisters, everyone present here in person and also virtually, we thank our Vice Chancellor. And only one point I captured is that Sir said there are 100 such more missions to go before we understand bit of sun. And 100 such missions will need a lot of effort. And this is, I think, one pointer to the academic scientific community of this university, students and faculty, that we can and we have a lot more to do. Thank you, Sai Ram. Over to our friends on the stage.
Om Shri Sai Ram, offering our collective pranams at Bhagavan's lotus feet. I take this opportunity to thank our respected Vice Chancellor Sir for giving us a lot of insights into this very prestigious maiden solar mission of the country. Thank you, sir, for illustrating various aspects of the Aditya mission and the role played by you and your team from the Indian Institute of Astrophysics. We are extremely proud that we have Sir with us as a Vice Chancellor, and I'm sure the younger generation should get inspired. As Sir rightly put it, there are 100 more missions probably we need, and we need the younger generation to get inspired and work towards this glory to be brought to our country. I thank you, sir, once again for this valuable time you have taken to enlighten us. I also thank the students of the Department of Physics, the second year MSc students, who have put up a very short but sweet program on the various basic aspects of solar energy and the sun, just as a prelude to this Aditya mission. We hope and pray sincerely to Bhagavan that this mission should be successful, and as we await the PSLV taking it all the way, and probably after 100 days we will get to know various aspects and the working of this mission. We pray that everything should go on well and bring a lot of scientific data back to the country and make the country proud. With these few words, I thank all of you once again for participating in this program, and we will end this session with Mangala Harati. Sai Ram. Just a minute.
श्रीकरा सर्वा प्राणपते स्वामी सर्वा प्राणपते आश्रितकल्पलतिका आश्रितकल्पलतिका आपद्बान्धवा ॐ जय जगदीश हरे पिता गुरुदैवमु मरियन्तयु नीवे स्वामी मरियन्तयु नीवे नाद ब्रह्म जगन्नाथा नाद ब्रह्म जगन्नाथा नागेन्द्राशयना ॐ जय जगदीश हरे ओंकार रूप ओजस्वियो साई महादेवा सत्य साई महादेवा मंगल आरती अंदुको मंगल आरती अंदुको मंदर गिरिधारी ओम जय जगदीश हरे नारायण नारायण ओम सत्यनारायण नारायण नारायण ओम नारायण नारायण ओम सत्यनारायण नारायण ओम सत्यनारायण नारायण ओम जय सद्गुरुदेवा नारायण नारायण ओम सत्यनारायण नारायण नारायण ओम नारायण नारायण ओम सत्यनारायण नारायण ओम सत्यनारायण नारायण ओम जय सद्गुरुदेवा नारायण नारायण ओम सत्यनारायण नारायण नारायण ओम नारायण नारायण ओम सत्यनारायण नारायण ओम सत्यनारायण नारायण ओम जय सद्गुरुदेवा ओम शांति 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 समस्तलोकाः सुखिनो भवन्तु समस्तलोकाः सुखिनो भवन्तु समस्तलोकाः सुखिनो भवन्तु ॐ शान्ति शान्ति शान्तिः जय बोलो भगवान श्री सत्य साई बाबा जी की जय। श्री गणेश